Isomerism and IUPAC nomenclature. There are two types of isomers: structural isomers, which are two or more organic compounds that have the same atoms but a different arrangement and bonding. This means that they will have the same molecular formula but a different structural formula. This type of isomerism includes branching and position isomers. The other type of isomerism is stereoisomers. These are two or more organic compounds that have the same atoms and bonding but a different spatial arrangement. This includes geometric isomers, which have different arrangements of atoms around a rigid double bond, and also optical isomers, which we will cover later in the unit. Nomenclature is a set of rules by IUPAC used to name organic compounds. The rules allow us to see a little bit about the arrangement of the atoms as well as what atoms are in the compound. IUPAC is the International Union of Pure and Applied Chemistry. In organic chemistry, the carbons are numbered. This allows us to see where any substituents are in the compound. For example, this is 1-bromopentane. It is important to realise that this is carbon number 1, not because it's on the left, but because that is where the bromine atom is attached. Similarly, this molecule is also 1-bromopentane. This time the carbons have been labelled from right to left. When we look at the molecule in 3D, we can see that it's actually the same, just turn around. So it's important that it has the same name. If we add in a double bond, this is no longer the case. This molecule is 1-bromopent-1-ene. Now, if we move the bromine atom to the other end, it becomes 5-bromopent-1-ene. This is because the double bond has ensured that this must stay as carbon number 1. Again, by putting the molecules side by side, we can see the difference. It is usual to number the carbons for the double bond first, and then consider any substituents afterwards. Where we have more than one substituent, we will name them in alphabetical order, with the numbers of the carbons just before the prefix. For multiple substituents which are the same, we can use a multiplier, in this case di, meaning that there are 2 bromine atoms. It is still important to number them. This is 1,2-dibromopentane. It's also possible to have substituents on the same carbon. It's still important to repeat the number to show that they are both on the first carbon. This is 1,1-dibromopentane. These are examples of position isomerism because the position of the substituent has changed. Another example of position isomerism is where the position of a bond changes, such as a multiple bond. This is but-1-ene and but-2-ene. These are the only two possible positions of the double bond, because as we can see, if we were to move it into the third position, this is just but-1-ene again. Once again, this can be seen more easily by looking at the model. So this is but-1-ene, and this is but-2-ene. The same can be seen with pentene, pent-1-ene and pent-2-ene. As we increase the number of carbon atoms in the chain, the number of possible isomers also increases. Once again, these are the only two possible positions for the double bond. That's because if we start to move the double bond further to the right, we're just repeating the same two molecules. The other type of structural isomerism is branching. This molecule is a structural isomer of butane. We can see that because it has 4 carbon atoms and 10 hydrogen atoms. The branches are called alkyl groups. They have the same molecular formula as alkanes, except for there is one less hydrogen atom. When naming branched molecules, we name the longest chain first and then add the alkyl groups as a prefix. This molecule's name is methylpropane. Propane because there are 3 carbons in the longest chain, and methyl because there is a branch containing 1 carbon attached to it. We would usually add a locant to show the position of the methyl group. However, that is not necessary for methylpropane. This is because if the methyl group were in any other position, it would simply be butane. Here's what methylpropane looks like as a model. As you can see, when we take into account the bond angle, it's actually symmetrical. For molecules with a longer main chain, we do add a locant. As before, the substituents can be in different positions. Here are the 2 available positions for methylpentane. Once again, we are numbering the carbons from the side which gives the lowest locant number. Here is 2 methylpentane with the methyl group on the second carbon. Here is 3 methylpentane with the methyl group on the third carbon. The third type of isomerism that we will cover in this part of the unit is geometric isomerism, which is a type of stereoisomerism. Geometric isomerism occurs because the carbon-carbon double bond is rigid and cannot rotate. Therefore, if different substituent groups are placed to each side of it, there can be 2 forms. Here, the letters A and B are used to show this. On the first molecule, the letters A are at the same side of the carbon-carbon double bond. On the second molecule, they are at opposite sides of the bond. On the same side is cis, which comes from the Latin on this side. When they are opposite each other, the molecule is trans, which comes from the Latin on the other side. Here is cis-butene and trans-butene. As we can see, the alkyl groups on the cis molecule are on the same side of the double bond. On the trans molecule, they are on the opposite side. This is a model of the cis isomer. As we can see, the 2 CH3 substituents are at one side of the double bond. The double bond does not rotate, so they cannot swap sides. This is the trans isomer. This has CH3 groups at opposite sides of the double bond. Again, it does not rotate, so that's permanent. What we can also see, if we put them together, is that the trans isomer is straighter than the cis isomer. This leads to more surface contact between the same molecules, which usually results in a higher melting and boiling point because more energy is required to overcome the van der Waals forces. As we can see here, but-1-ene doesn't have any geometrical isomers. That's because the carbon-carbon double bond is at the end of the molecule, resulting in the end carbon having 2 hydrogen atoms. In order for geometrical isomerism to occur, both carbons in the double bond must have two different substituents attached to them. This is butanene. As you can see, there are two hydrogens on the end, so even if these were switched around, it would be the same thing. Pent-2ene does show geometrical isomerism. It doesn't matter that the two groups on the carbon atoms are different from each other. Here we have CH3 and here we have C2H5. Because there are hydrogen atoms on the other side of the carbon-carbon double bond, we can see that this is the cis isomer and this is the trans isomer. We can also see geometrical isomerism in molecules that have other substituents other than hydrocarbons. In this case, these groups can be on the ends of the carbon chain. Here is cis 1-chloro-2-iodoethene and trans 1-chloro-2-iodoethene. Notice that even though this is a very short molecule, we still require locants for the chlorine and iodine substituents. This is because it would be possible for both of them to be attached to the same carbon atom. In this case, it would be 1-chloro-1-iodoethene.